Okay, let's unpack this. Today we're doing a deep dive into some source material about the really fundamental world of sets. We're assuming, you have the basics down, but we really want to dig into the relationships between sets and some core operations too.
Yeah, the goal isn't just definitions, right? It's understanding the structure. Like,
Yeah.
what does it actually mean for one set to be inside another?
Exactly. Or this idea of a universal set.
And how we manipulate them, combine them, compare them.
Right. So based on this material, we'll hit subsets, supersets, proper subsets,
A universal set complements.
and then union, intersection, difference, the classics. Let's just jump in.
Okay, inclusion first. Subsets. The basic idea, if you remember, is if every single element in set A is also in set B.
Then A is a subset of BA, subset B.
Yep, the source had that simple example. A is 2, 4, 6, and B is 1, 2, 3, 4, 5, 6, 7.
In either case, all of A's elements are right there in B.
Which, conversely, makes B the superset of A. B contains A. B will subsetec A.
Okay, but then there are those rules that sometimes trip people up, like any set is a subset of itself, a subset dollar.
Absolutely. And the big one, the empty set, APA, is a subset of every set. Always.
Why is that one so, foundational?
Well, think about the definition. A is a subset of B if there are no elements in A that are not in B.
Okay.
The empty set has no elements at all. So it's impossible for it to contain an element that's not in B, whatever B is.
Ah, right. It can't fail the test because it has nothing to test with. It satisfies the condition by default, sort of.
Exactly. Trivially satisfied. It's crucial.
Okay, so building on subsets, we get proper subsets. Whittle subset BB,
Right, this is a stricter thing. A is a subset of B, and A is not equal to B.
meaning B must have at least one element that A doesn't have.
Yes. Or, as the source puts it, the number of elements, NA, has to be strictly less than NB.
So for AB, the subsets are AB and AB, but the proper subsets are just A and B. You leave out the set itself.
Precisely. Which leads to that neat little formula from the source.
Oh yeah, the two Mendele thing. If a set has an elements
It has two non-total subsets.
and two Delambroder's proper subsets, because you just subtract the one case where it's the set itself.
It's kind of wild, isn't it? A tiny set, like 3 elements, gives you 283 3-lars, so 8 subsets.
8 different ways to group them. It shows how fast complexity grows.
It really does.
Yeah.
Okay, so to manage all this, we need context. The universal set, usually written $10 or U.
This is the universe for whatever problem you're looking at. Everything relevant.
Exactly. And the key thing the source stresses is that it's not unique. It just needs to contain all the elements of the sets you're currently discussing.
Right. So if we're talking about vowels, the universal set might just be A, E, I, O, U, or maybe the whole alphabet. Depends on the situation.
Perfect example. And within that defined universe, we get the complement. A prime, A ida.
Which is just everything in the universal set that's not in A.
Yep. Example from the source. Universal set sexity is 1, 2, 3, 4, 5, 6, 7, 8. Set A is 1, 3, 5, 7.
Then A must be 2, 4, 6, everything else in that universe.
Correct. It's like the missing pieces needed to make up the whole U.
So A and A have zero overlap. They're disjoint.
Within that U, yes. And logically, the complement of nothing is everything.
And the complement of everything is nothing. Makes sense.
Okay, last bit. Operations. Sets aren't static. We can combine them.
First up, union. A cup to butter.
This is the OR operation, basically. You take everything in A or in B or in both, just lump them together, remove duplicates.
So 1, 2, 3, 4, 5 is 1, 2, 3, 4, 5.
Got it. Then intersection, a captable.
This is the A and D part. Only the elements that are in both A and B, the overlap.
Right, like apples, bananas, grapes is just...
Banana is the only thing they share.
Exactly. And finally, difference, AB.
Okay, this one's a bit different. It's elements in A that are not in B. Start with A, take out anything that's also in B.
Precisely. So red, blue, green, blue, yellow.
You start with red, blue, green. Remove blue because it's in the second set. Yellow isn't in the first set, so ignore it. You're left with red, green.
Perfect.
So wrapping up, we've seen how sets can be nested, right? Subsets, proper subsets.
And how the universal set gives us that crucial frame of reference.
Which then lets us define the complement what's not in a set.
And finally, these operations union, intersection, difference let us actively, combine and filter these collections based on their elements.
It might seem basic, but this structure is everywhere. Organizing data, logic.
Absolutely fundamental.
And just think about that $200 rule one more time. Even with just, say, 4 elements in a set, 2430s is 16 subsets.
16 different combinations or ways to select from just those four things.
It really makes you wonder, doesn't it? How quickly possibilities multiply, and how we even begin to think about or manage all the potential combinations that arise from even small collections of items or ideas.
That's a great point. The combinatorial explosion is real, and these basic set concepts are the first step in trying to tame it.